Okay, and we usually can plot the truncation error in finite difference using that way. So let's say this is my delta x. I'm plotting this in log scale. Okay, it usually goes from, let's say, 1 to 0.1 to 0.01 to 0.001 to e to the minus 4, e to the minus 5, etc. Right? And this is my truncation error. It may also go from like 10 to 1 to 0.01 to 0.001, something like this. So if I have the truncation error that goes like this, that is proportional to delta x squared, how do you think the relationship looks like in a log scale? And a straight line with a slope of 2, exactly right. So you need to, this is very important because that is the way you usually numerically quantify how much error you're producing. Okay, so usually, for example, if you know the true solution or the true derivative of a function, and you compute it numerically, also use a finite difference for the approximation, and you look at the truncation error. And how do you know your implementation, your MATLAB code is correct? You plot the truncation error like this. If it goes, so let's say if you implement this scheme and you plot the truncation error, and you find a line that goes like this. You plot one point, another point, another point, another point. It goes like this. Do you think your MATLAB code is correct? So connect them, it'll be a line like this. This is the slope of 1. That means you have a bug. So it's very easy, especially in high order schemes. It's very easy to have a correct behaving code that actually doesn't achieve the order of accuracy you want. And that is one way to detect it, is to actually plot the order of accuracy, is to plot how fast it goes to 0. A correct code, even if it stopped higher, it should go down by about 2 orders of magnitude per order of magnitude of delta x. So it should go up to here for every time you decrease the delta x by a factor of 10. And then it goes to here. So you should have a line that looks like that. And if you compare a first order scheme with the second order scheme, you're going to see initially maybe the second order scheme makes bigger error. But finally, as I make delta x smaller and smaller, it is going to become more accurate. All right. Yes, this is for one particular u. This is for a given u, right? So if you make u more and more complex as you refine the grid, this wouldn't be true, right? So this is for one particular u. And another thing is that there are these high order terms, which is ultimately going to become not important as delta x is small enough. But initially, in the beginning, it might not be like this. So you may see another scheme that is second order. You may see another scheme that behaves like this. It can be here, it can be here, it can be here, and then it goes like this. So if you connected the line, it may go like this. But this is still second order because the asymptotic slope as delta x is small enough is the right behavior. Initially, it may not look like a slope of 2 because I still have these high order terms that may not be small when delta x is large, right? So these are very good checks for you to have a confidence that you have the right implementation, you have the right derivation of your schema and have the right implementation. Okay, I'm going to say a little bit on how to construct finite difference approximations. Question? Yes. Yes. Right. That's a good point. So the truncation error for a numerical solution is something you can never compute exactly. This type of error analysis is called a priori error analysis because you need to assume an analytical solution for this to work. But in most cases, you don't know an analytical solution. It may not even exist. So this type of analysis, the value of the analysis is really this, right? It's really to have a confidence of how fast does the solution go to zero as you refine the grid. There is a more advanced type of error analysis called a posteriori error analysis. The goal of that type of analysis, we're going to discuss it in the finite element part of the lecture. The goal of that analysis is to write the truncation error not as a function of the analytical solution, but as a function of the numerical solution. So that type of an error analysis is much more difficult, but it can actually give you a computable bound on the error. And in that case, you can't usually write the error equal to something. You usually write the error less or equal to something. So that's a very good point. Any other questions on this?